Folks can hear me? So this is technically a workshop, which means that there's code you can do on your laptops if you want to pull open your laptops and do stuff. If anything that you're doing doesn't work during the demo, don't tell anybody. No, I'm just kidding. Now, if it doesn't work, this is a workshop, so please stop me. Let's ask questions and try to make it actually work. This is the link. In general, I hope to keep this very informal. It's the end of the day. We got 75 minutes. The goal is to actually talk about the interesting stuff that we're trying to do here. So please interrupt me at any point in time to ask questions, and let's try to have fun at the end of the day. All right. Anybody else? Can I move on? Does anybody else want to look at this link more, longer? Can always come back to it. We good? Almost? Almost? It's already interactive. I love this. Great. Okay. All right. So the best way to play with that code for that link that I just sent is either locally on your laptop, or you can also fire up CodeSpace on GitHub. How many people have ever used CodeSpaces? Just curious. Okay, one, maybe two, 1.5. Okay. Yeah, they're pretty interesting. One of the nice things about them is that we've included a dev container that just includes all your prereqs, so you can fire up the CodeSpace and you have everything you need. If you use dev containers locally, there's a dev container in there, and you probably know what I'm talking about. You can grab it, you can fire it up. If not, this is some of the prereqs. Really not many. If you want to run the TypeScript code for a backend, you're going to need Node.js version greater than 20. I'm going to be showing all the demos that I do with the Python code, and that requires Python 3.10 or greater, and we use Rye. You could use pip or any other tool, but we just happen to use Rye, and we've got all the documents set up in Rye. Okay, next question I wanted to ask is, I'm curious, how many folks in the audience are application developers versus more ops, infrastructure operators? So let's start with application developers. All right, we got all right, more ops. We're on the ops side. Okay, all right, what about both? People are like, I have to do it all, because that's how software tends to be built. All right, we got it, okay. All right, yeah, so, yeah, great, let's dive in. Okay, so just quickly, who am I? So my background is, I was one of the creators of Apache Mesos, which was a container orchestrator before Kubernetes. It really helped to ignite the container orchestrator space. It was used massively at Twitter, and then Uber, Netflix, Apple. These days, if you tend to see a post about Mesos, it's usually one of these really big companies moving off of Mesos and onto Kubernetes. But in the heyday of Mesos, we were running on tens of millions of cores. It's kind of become like the BSD in the Kubernetes era. I co-founded a company called Mesosphere. We did a lot of really fun stuff in the early days of cloud native, but maybe one of my favorite things we did was at a KubeCon, we hosted IceCube for IceCubeCon, which was a really, really great party. Did anybody go? Does anybody from this audience happen to be? All right, but you, yeah, that's right. We co-hosted, great. Anyway, tons of fun, but we actually did a bunch of really cool stuff. That was just a standout. I was one of the founding board members of the CNCF with Chris A, and on the first TOC. So had a really good time getting to see a lot of that blow up, and that gave me a lot of time to think about cloud native and how we build apps. So I've been thinking a lot about how we can make it better, and now I'm doing that with Reboot that I'm going to be talking about today. Yeah, so I was doing some reflecting, and you know, when I thought back on the early container orchestrators and why we were building them, we were really building them for the operators, for the infrastructure teams, more so than we were building it for application developers. You know, in fact, we were actually asking application developers to do a rather bizarre thing, which was to break their applications into a bunch of smaller pieces, because that was better for us as the ops folks. It let us do things like bin packing. It let us do things like do software and hardware upgrades if we had physical machines or virtual machines. It lets provision and deprovision resources as we wanted to, and to really make that work well, we needed to ask the application developers to break up their apps. And they did it, surprisingly enough, because the juice was really worth the squeeze. But it was a pain in the butt, and I think there's a lot of persisting challenges in the way that we build cloud-native applications that continue from the beginning to this day. So this is, kind of the big theme that I'd spent a bunch of time thinking about was, Kubernetes and container orchestration in general gave infrastructure teams an abstraction for their machines so they could treat them like cattle rather than pets. I'm sure you guys have heard that term. And the question that I've been asking myself a lot is, what's the right abstractions for application developers so they can do the same thing but for their business logic that runs on top of the container orchestrators? That's really the motivator behind the work that we're doing with Reboot. And another kind of succinct way of maybe asking that question is, like, what comes after microservices? Is there some other abstraction, some other way of building cloud-native apps that's not microservices? And if some people are thinking, well, maybe it's serverless, which we thought at a time it was going to be. We thought when we first were thinking about just writing lambdas or using serverless architectures that that's what everybody would be doing. I think we all realize that's not the case, and we'll talk a little about why that is. But these are really the questions that we were asking. So to be clear, microservices, and throughout the rest of this talk, when I say the word microservices, I'm probably really referring to microservices or serverless microservices or lambdas. They have a lot going for them, right? The modularity of breaking your app into a bunch of different pieces makes it easier to understand those pieces, to modify them, to test them. It gives engineering organizations agility because those teams can operate and deploy their software independently, autonomously. I'm sure this is all stuff you guys know, that you've drank from the fire hose, which is why you're at a KCD. It enables technology diversity behind well-encapsulated APIs. If you're an organization that wants lots of programming languages, you can have it. And all of that makes it easier to scale your applications and the company. And yet, even to this day, the conventional wisdom out there is that microservices is not the place you should start. And this is what we tell so many organizations. There's a great quote from Martin Fowler, you shouldn't start a new project with microservices even if you're sure your application will be big enough to make it worthwhile. Which means that for a lot of organizations, when they go to move to microservices is the same time that their company's product and teams start to scale like crazy, which is really ironic because that's the last time that you want to be thinking about completely rewriting your application, is when you should actually be focusing on everything you need to be doing. So there's a huge disconnect here, which is we've got a way of building software for the cloud that we're actually telling people not to do until you need to do it, but then that's the worst time to do it. When you think about Martin's quote, there's a lot of things that might come to mind about why microservices are not the right architecture. And there's lots of talks that have happened today and lots of talks that continue to happen at a bunch of these kinds of conferences that talk about all the things you have to do around the application to run the application. And that's not what I'm going to be talking about today. I'm specifically going to be talking about where I think Martin was really coming from, which is the application architecture itself and the challenges of just building the application itself. And that being the core foundation that we can put all the other stuff around, CI/CD and everything else around, but getting those primitives right is what this talk's really about. So I'm going to talk about 4 persisting developer challenges, and I'm going to talk about how, for each of them, I'm going to talk about how we can solve those problems in today's world, and then how we're solving them in Reboot. And the goal of Reboot is we're really, again, trying to think in the future. What could a programming model look like for after microservices? And I hope that as part of this, my goal is not that you are like, oh, I should go use Reboot. All that would be cool. We'd love the feedback. The goal actually is really to get people to start thinking differently about how we can actually build our applications for the cloud. All right. So the 4 developer challenges I'm going to talk about. One is conflation of code and deployment. And I'll talk about what that means in a little bit. The next is, it's still hard to do queries, and it's prohibitively hard to do real-time queries. The next is what I call the retry paradox, which is a thing that we all want to do, and it's surprisingly hard still. And the last one is weak consistency. And these are kind of my themes for these bigger problems that I'm going to go into in detail. So throughout the rest of the talk, we're going to kind of go from 100,000 foot down to 1,000 feet, and then back to 100,000 foot, and back and forth. So conflation of code and deployment. I think this one's really interesting because, as I was mentioning, microservices to something like serverless could be seen as an evolution of better abstractions for building apps. And one of the big things as that part of evolution was with serverless, you didn't have to write as much YAML. You just got to focus on your function, and then that function got deployed, and there was some kind of an execution model for how that function would actually get run. This conflation of code and deployment is a huge challenge for developers, that they have to focus on the two things. And the future that we'd like to see is one where that's not something that developers have to focus on. They can just focus on their business logic. The second two, I like to kind of group into this funny thing, which is when we were thinking about the apps that we were going to run on Kubernetes, we weren't really thinking about the full stack. We were really just thinking about the back end. While we did a lot of stuff on the back end, we actually just made the front end talking to the back end even harder, which just made building applications even harder. There's a great article out there called "There's Just No Getting Around It, You're Building a Distributed System." Has anyone seen this article or read it? It's from about 2011, I think. And what I love about this article is, it's 2011. This is pre-microservices. So the distributed system that they were really talking about was the one between the browser and the monolith. That was the distributed system. And we just made it harder. That was a hard problem we had to solve then, and we just made it harder with microservices by making everything even more of a distributed system, making it harder to do queries, making it harder to figure out the right way to do retries, and effectively making our apps more and more weakly consistent. So this is all about distributed systems are hard. A future kind of higher level abstractions, we want developers to focus on the business logic, not on deployment. It should scale when you need it, so we can avoid Martin's quote of like, you shouldn't use this till you need scale. It should work great at small scale and scale when you need it. It should be full stack ready to make sure that we're thinking about the front end as well. And finally, it should be safe by design. So the challenges of building distributed systems is hard. We want to make it safe. Okay, so now we're going to start to get into some more, a little bit of reboot, and then we'll kind of dive back into those challenges. So what's reboot? It's an application framework with a novel cloud-native programming model. So we're trying to focus on a better way to write cloud-native apps. It's not a new programming language. Okay, so you can use TypeScript, you can use Python. That's what we're going to do in the examples here. But it is a new programming model, which means it's a new way about thinking about writing those apps. And there are certain rules and constraints that you have to follow. You can read more about it at reboot.dev. There's some pretty good docs at docs.reboot.dev, and you can join our Discord. Okay, so for this workshop, like I said, I'm going to be doing everything in Python. If you've got prereqs set up or a code space created, these are kind of the steps for running things in your environment. I'm going to be switching back and forth between the browser and code. How's the font size? Visible? A little bigger?
A little bigger, please. I didn't bring my own main classes.
Yeah, better? Okay. So I'm going to be switching back. If at some point you can't say something again, just please interrupt. Questions. Let's keep it flowing. If you are launching a code space, you might need to do some manual port forwarding. Again, please pause me, ask questions. We can try to get stuff set up for that. Okay. All right. So what's reboot? From 100,000 feet, reboot is an application framework with a new programming model. This is hopefully some of the fun stuff, the fun part of the talk, to get you to think differently about how we could build apps for the cloud. Reboot's really two things. It's data, and it's functions, which is kind of all apps, all programming models. But particularly, it's an execution and composition semantics that actually make building apps safer and easier for full stack consumption. Okay, so I'm gonna dive into each of them. So reboot data. So the way you can kind of think about a reboot application is it's sort of like a gRPC application. How many people here have built gRPC applications? Do we have any gRPC users? A couple? Okay. So gRPC is a pretty standard application development tool in the cloud native ecosystem. In Reboot, you describe data types using protobuf. gRPC also uses protobufs for describing their APIs. Okay, these data types are things like account. So the example that we're going to be doing, if you've looked on your laptops, is a bank. We're going to be implementing a full stack bank-like app. And so you can imagine that one of the types we might have would be, say, a user's account. Account might have things like, say, the name, birthday, balance, so forth and so on. Okay? So first, data is typed. In Reboot, those pieces of data are durable. So when you construct new instances of them in the code that you write, they persist. They're orthogonally persisted. What I mean by that is you are not responsible for persisting them. You are not calling to some database and say, store this. As part of the programming model, as you'll see, when you work with these pieces of data and you update them, when you make updates, we take care of persisting it for you. Okay, so question, yeah?
Where?
We persist it in a database, but you are not managing the database. Okay, so it's in a database, yeah. All right, okay. Reboot data types are, they're addressable. Okay, so when you construct one of these things, everyone has an ID. And you can use that ID to actually then call functions for that type. Okay, so you can get references to them. So again, I can get a reference to my account, and then once I have that account, I can make a function call to it. And then finally, the way you can think about these data types is that they're naturally partitioned based on those IDs. Okay, so if I have many, many instances of accounts, those might live on many, many different machines. And again, what we're trying to do is we're trying to create a higher level abstraction, get developers focusing at the business, at the logic layer, at the code layer. And so we're trying to create an abstraction that lets us do smart things about deployment that can change dynamically over time without the developer having to care about it. Okay? Because for the most part, you don't need to care about where these data types are partitioned, provisioned, running. They can be tiered. You can have grandma's account who logs into the bank once a year, live 99.9% of the time in cold storage, and only needs to be running in one of these machines in a partition when she logs in. Right? So really, most of the time, you don't need to care until you actually do. That's out of the scope of the talk. We have ways of making it so you can care about where the data might live. You know, all good abstractions, I think, are leaky abstractions, where ultimately you can peel back the covers and make more of the constraints you want to make. But for the purpose of this talk, we're not going to talk about that. Okay? All right, so reboot data. So there are these objects. They're typed. They're durable when you get them created. They're persisted. They're addressable, and they're partitioned. Okay? Functions, again, follow very similarly to gRPC. You describe the functions that you can perform on a reboot data type in protobuf using the interface definition language. So you can imagine things like account. You're allowed to do things like deposit to the account, withdraw, get its balance, open an account, so forth and so on. But reboot functions are also qualified. And what I mean by that is that their execution and composition behavior is specified explicitly. So you can kind of see this. We've qualified deposit as being a writer, withdraw as being a writer, balance as being a reader, and open as being a writer. And I'm going to talk more about that, but that plays into the execution and composition semantics that actually makes it safer to build these apps in the first place. Okay? Okay, so reboot at high level, data and functions with a particular execution and composition semantics, and now I'm going to talk a bit about those execution and composition semantics. So just like gRPC, the way that you actually implement your reboot methods is you implement servicers. For those that are familiar, the code on the left-hand side is actually the code in Python for implementing a gRPC servicer that would map to this protobuf specification. On the right-hand side is what it looks like when you're using reboot. So really, really similar, with the big difference being that every single one of these methods, in addition to getting passed a context and a request, also gets passed a state. And that state represents the instance of one of those types that had been constructed that we're calling this function on. Okay, so if I construct an account and then I want to call its deposit, some code will run in the cluster, this deposit method will run somewhere on Kubernetes to implement this, and the state that gets passed to it is actually the persisted data that represents that account. Okay, and you're going to see some more examples of how that looks. Okay, so I'm going to talk a little bit about readers and writers just to give a sense of reboot and how it works, and then I'm going to go back to those persisting challenges and talk about how we actually solve them in reboot. Okay, so a reboot reader. So as I mentioned, balance is a reader. So how do readers work? What are their execution semantics? So readers are passed the immutable snapshot of the state for that instance, the account instance in this case. And so they can read from that state. They can read the fields, they can do whatever they want, but they can't mutate it. If they were to change the field, it wouldn't have any impact. Because they're passed an immutable state and they're not making any changes, we can execute them concurrently. So we can run many readers simultaneously. And readers, their bodies can only call other readers of any other types. So they can't call anything else. That's where the qualified part of the programming model comes in. So readers can only call other readers. Okay? And we're doing that because we're trying to eliminate effects, which is going to help us build a safer, distributed programming model by default. Okay? That's readers. All right, writers are very similar to readers. They get past the current state. However, you can do updates with writers. In this case, deposit, what's it doing? State.balance, we're adding the amount that's being deposited. And so therefore, the programming model you can think about is they're executed serially. So per instance of one of these accounts, only one writer can execute at a time. That allows them to mutate the state directly. Now what can they do? They can also only call other readers. They can't call the writers, they can only call the readers. And you're going to see why that's actually really, really important in the future, and why in today's land of building microservices, we get bugs all the time when we write code like this when we don't have constrained models. Okay? All right. The way the state works is at the end of the function, when you return a response, that state is orthogonally persisted. Okay? And by orthogonally persisted, I mean we, the runtime, take care of persisting it for you. Okay? All right. All right, so we've got some semantics that I've already told you that we have to make sure work, okay? So one is that you can only call allowed functions. So, writers and readers can only call other readers. How do we make sure that that happens in practice? We do that because there's this other field that gets passed to every single function, which is a context. Okay, in this case, for writers, you get passed a writer context, and for readers, you get passed a reader context. And if, say, what you tried to do was get a reference to one of these other types and then call one of their methods on it, like if I, inside deposit, tried to get a reference to another account and then called deposit on that account, I would get a type error. Because I can't, with my writer context or with a reader context, call another writer. The only thing I'm allowed to do with those contexts is call another reader. And that's how we can tell developers, as they're building their apps, that they're safely following the semantics. They can only call the required functions. So we guarantee that every single writer has one set of effects that occurs, and those effects are just the updates to its state that happen at the end. Okay? Well, we want to make sure that there's not any other side effects that are happening as well, because the elimination of these effects is what's going to make a lot of other nice things play out that are going to solve a lot of these persisting developer challenges. So we want to make sure that even though you can't do something like call some other account's deposit, that you don't call to some third-party database or to Stripe or some other thing where you might have some kind of external effect, okay? And so we do that when you're running reboot.dev, which we're going to show in a little bit here. In the reboot.dev mode, what we actually do is we execute every single one of your methods twice when they get called. So when a request comes in, we just call your function twice. And if you're doing something in that function that's an external side effect, you're going to find out really quick, and you're going to stop doing it. If we had a new programming language, this might be something that we could actually prevent people from doing with, say, a really sophisticated type or effect system. But we don't. We're trying to make this work for all of us just building systems with TypeScript, Python, and the existing languages. And we actually got this idea from React. Anybody here ever built a React front-end based application? Yeah, so have you heard of strict mode in React? So strict mode in React is where React actually reruns all your components twice to make sure that you put all your effects in something like a use effect handler, okay? React actually inspired a lot of ideas around the reactivity that we did here. It's a great example of a piece of tech that, rather than trying to introduce some crazy new type system, introduced some really basic ideas that worked for the masses super well, and this is what we're doing too. Okay, all right. So hopefully you have a little bit of understanding about kind of reboot and the programming model and what it looks like and how you're building things. Now we're going to talk about some of these challenges, how we're solving them today in cloud native, and how we can solve them in reboot. Okay, so configuration of code and deployment. Okay, so I think there's a great quote that really captures this the best, which is from Sanjay Gemwant, where they wrote a paper in HotOS where he says, microservices conflate logical boundaries, how code is written, with physical boundaries, how code is deployed. So as an architecture, it makes us think about both when we're writing the code, instead of just getting to focus on the business logic, right? And the challenge of this is it makes it harder to build the applications. It makes us have to think a lot about those deployment pieces when most of the time we shouldn't be caring about it. The future that we'd like to see, the higher level abstractions, developers should be able to write their applications logically as monoliths, right? But in such a way that a runtime can decide how to distribute and run the application code across resources. And again, what serverless did was it gave us an abstraction, the function, where we didn't have to think so much about deployment. It gave us a programming model for it, which is like, hey, if you need to run more instances of this function, I'll just spin up more instances of this function. Okay, so that's the future direction that we're trying to think about with these high-level abstractions. So what is the state of the art for doing this in the cloud-native ecosystem today? Probably, the two pieces of tech that I think best exemplify this are something like Dapper Actors, which if anybody went to the actors talk earlier, they got a sense of what actors look like. So actors are a higher level abstraction that you write that then the runtime decides where it's going to run, how it's going to move it around, so forth and so on. A lot of what Reboot has done is it's actually inspired by a lot of the actor ideas, but it's trying to solve a lot of the pitfalls with building actors right now when it comes to some of the other problems that we'll talk about later in the talk. And then the other project that I think really exemplifies this is Service Weaver. Anybody heard of Service Weaver? Okay. Unfortunately, it's a project that's being shut down, but it was a project that was created by Sanjay Gemwant and others at Google, and this was where they were pushing this exact idea, which is, hey, how can we make it so you can focus on just writing the code, and then we'll be responsible for deciding where to actually place all of your pieces of code and run them. I think this will be the future. I think that in the future we will be able to just write code and there will be runtimes that think about how we place it, and I think it will be hugely advantageous for developers who don't have to be thinking about anything or writing YAML. That doesn't mean that they're not going to care about certain placement-like things. I just think that those things will come from a leaky abstraction where most of the time you don't care, but sometimes you will. You'll go into the abstraction and in code you'll specify what you want. So I kind of threw autoscaling in there. Autoscaling is helping you to not think as much about deployment, and it will be a part of any future system. This is our bank's main. And basically what we're telling the Reboot runtime is that these are the different servicers I want to run. I want to run an account servicer. I want to run a bank servicer that's implementing the methods for account and bank. as well as some third-party servicers. These are just libraries that I pulled in that are also implemented using Reboot. So there's one for Mailgun. Mailgun is an external service for sending emails. I've got a collections servicer, a sorted map. I'll talk about how I use that in a little bit. I've got one for memoizing results of stuff. Anyway, so I just specify all these things, and that's it. I've just basically said, here's all my code. Now the runtime, you be responsible for deciding how all this code runs and where. Okay? Now, when I ran this, I didn't specify anything locally about like how to think about this running as a distributed system, but I could have. If I wanted to, I could have actually said, you know what, run this as 8 partitions, or 4 partitions, or 2 partitions, or whatever I want. So even locally on my laptop, I can get the experience of many partitions, the data being distributed across them. So I'm getting the experience of building my app the way it will ultimately be run somehow in the cloud across a bunch of resources. Okay, so I'm not gonna do that. I'm just gonna keep jamming. Okay, all right. Oops. Here we go. Okay. All right. Let's move to the next one. Starting to get to some of the more interesting one. Queries in real time. Okay, so this is really queries real time. Okay. So let's start with queries. When you first start building microservice or Lambda-based applications, the picture on the left is what is presented as what your architecture is probably going to look like. It's a couple of boxes. I'm going to call between the different services of those boxes, and everything's going to work out great. In practice, the picture on the right is what all those microservices end up looking like. It's a ton of different services. There's crazy calling patterns. There's lots of different places where state is distributed, and you've got to extract that state out. Okay, making a query where you can get all that data, especially from the front end, is challenging. Okay, there's lots of different state-of-the-arts for doing that in the cloud-native ecosystem today. But most of the time, what we really do is we practice API composition. So we tend to build services that are responsible for calling out into a bunch of other services to aggregate the data that we want, take that data, and then serve it back to the user. Possibly storing it as a view, so we can render it back to the user faster, or just doing it in real time, perhaps just keeping it in memory. All right. Sometimes we need to push this pattern even farther, and we'll do it with something called CQRS. Which is, again, where you're actually going to be storing those views. Perhaps you're listening for other services so you can get updates when you want to construct those views. This is the stuff Martin Fowler was talking about. This is the stuff that, like, you can't just build your app. When you want to start building the app and thinking about these real-life things from a architecture perspective, these are the kind of things you have to do. I actually stole these pictures from this great blog post called Microservices Patterns. Queries. These are really the state-of-the-art ways that we're doing these things, okay? That's queries. That's the easy stuff. We're actually doing that in all of our apps. Now let's talk about real-time. How do we get real-time updates using these queries with state that's spread out across microservices? It's so challenging. It was challenging enough to figure out how we're going to call these different things. Now we want to somehow call these different things and get updates from all these different things when their state changes, so we can propagate that state all the way back up to, say, our front ends. There's no state of the art. It's a lot of queues and gluing and who knows what else, and for the most part, it just doesn't happen. Okay? So this is one of the big motivators. The best apps out there are real-time. That's the best experience, and so people have to jump through pretty big hurdles to make this work, and it's something that when we were building Reboot, we wanted to actually think about on day one. Okay, so we made real-time queries be a first-class primitive in Reboot. We introduced this thing called transactive reactivity, inspired by React, where React has this notion of reactivity in the front end. We wanted to push that reactivity into the back end. Why not? Push it all the way through. Okay, so this is going to be the first example I show of some code. So we saw the application main. Now we're going to look at one of the functions. Okay, now what I'm going to actually do is I'm going to sign somebody up. Who can I sign up? Somebody want to give me their email address? I'll sign myself up first, just so you know it's safe. Then who else can I sign up? Yeah.
Andy Suderman, S-U-D-E-R, D-E-R-M-A-N, .dev.
Sweet. Awesome. All right. We're going to give you a bunch more money. But not too much because of a demo we're going to do a little bit later. All right. Okay, cool. So you'll notice right away something interesting about the page, which is it's real time. Andy just got another $1 deposit in his account. So did I. This is the best bank. You all want to be part of it because the interest is real. It's going up. Okay, so now I want to look at the code about what's actually happening. So first, we're going to switch, we're going to switch back here to the bank front end, okay? Okay, so the backend function that we're actually calling to get this information in the front end is this function called account balances. So what's account balances doing? So account balances is looking up one of these reboot types, a sorted map, which is just all of the accounts that are in the system. You can think about it, you can think of it like a big distributed dictionary, okay? Then for each of those accounts, it's looping through them, and it's calling for each one, calling on the account to get its balance, pulling out the balance amount, sticking it in this pair basically, and then returning the pair. Okay? And in particular, so every single time that this function gets called, if it gets called reactively from the front end, what we're doing is we start building up a DAG of what's happening in this function call. Okay, so the bank calls into account. Maybe there's 2 accounts, because we had 2 accounts, so forth and so on. In fact, there's other types we're looking at as well. We're actually calling into the sorted map. That's a whole other type that might have state that would potentially change. Okay, and the fact that this is a reader, account balances is a reader, and as I talked about earlier, a reader has no other side effects, allows us to re-execute these readers just when the state changes. Okay, so anytime that state changes for any of these possible data types, these states that we touched anywhere in the system, when that state changes, functions are re-executed, their results are propagated up to anybody that had called those functions are re-executed, so forth and so on, ultimately all the way back up to the front end. Okay, so let's look at what the front end code looks like for this. So the front end code looks like this. How many, I think I saw some hands, we have some React developers, right? Okay, so in React, we generate code, thanks to this being in an IDL, protobuf, we generate code where for banks and accounts, we basically generate code for React developers to be able to make calls directly into the backend. So use is a prefix in the React ecosystem, which means this is going to be a reactive thing. So I'm using the bank with a particular bank ID. And in particular, I'm calling the account balances method, but I'm using the account balances method, which means I want to call account balances reactively. So that's it. These 2 lines of code now give me the account IDs and their balances reactively updated any single time that something changed in the background. So there's a lot of magic under the covers, right? There's WebSockets, there's connection management, there's diffing values back and forth. There's all the things that if somebody actually wanted to try to implement this, they would have to be doing that we're trying to provide right out of the box with this transitive reactivity. Okay, so really pushing reactivity from the front end into the back end. Okay. Yeah, so how can I call a function reactively? We generate it. You could also call it outside reactively if you wanted to. Lots of machinery. We're trying to handle it all for you. All right, moving on. I'm going to go to the retry paradox. All right. All right, so we're going to go back to 100,000 feet. We're going to talk about this problem and how it's being solved in state of the art and how we're solving a reboot. This is a problem as old as the beginning of building even just monolithic-based applications that we have today that we just made worse, as I talked about earlier, in a microservices-based world. When I run into bugs like this, I try to actually take, when I run into possible bugs, I try to take screenshots to see if it's going to end up being a bug, and in many circumstances it is. All right, so here I was trying to deposit a check on some nice Saturday afternoon, and I got a failed to deposit check. Okay, or try again. Naturally, since I was trying to deposit my check, I clicked try again. It said success, the check had been deposited. 24 hours later, I was rewarded with the fact that I had taken that screenshot, because I got an email that said we were unable to process your mobile check deposit. Please give us a call. So I gave them a call, of course. I said, what's going on? And they said, hey, you tried to deposit your check twice, which in, I think, 5 or 7 states in the United States of America is actually a felony. So they politely accused me of bank fraud. And I said, oh, no, I know. This is a hard problem in computer science. It's surprisingly hard. She didn't know what I was talking about, and I just said, never mind, let's move on. It's what I call the retry paradox. You want to retry calls in the event of a retriable error. That's what you want to do when you're building systems, like a network failure. That's a retriable error. I don't know what happened. I want to retry because I want to deposit the check. But we can't retry, because if the call has effects, you only want to make sure those effects are performed once. Right? That's why so many websites that we continue to go to today continue to have things like activating your session, please don't close this window or use the back button. We're confirming your booking, please don't close the browser or use the back button. Right? This is the state of the art from the beginning of time till now. Okay? So how do we solve this? How do we solve this problem? Have you guys solved this problem for your companies? Like, what are the things we have to do? Here are the big ones that I see, again, from sitting down and working with all these companies that are adopting cloud native, where, again, if they haven't done anything like this the first time when they've, say, bought our product, Mesosphere, Kubernetes, container orchestration, and then they run into these bugs, mostly what they say to me is like, why did we ever decide to do this? Like, how are we going to solve these problems? These are real problems. Our customers are calling us with bugs because people are depositing checks twice. All right. So we have to introduce things like queue or pub sub. So rather than be able to just make a call when you're trying to deposit a check, we'll say, you know what? We'll just try to write to a queue or to publish some event that says, hey, this event is that they're depositing this check. And then we'll do the actual processing later. So the only thing we'll really try to do is just that event. And ideally, we can do that event idempotently because the problem still exists. If I'm writing to a queue, it's no different than calling some service because I still only want to write to that queue once, right? Event sourcing is a variant of it where we keep the events forever. If we do start doing it this way, though, we've just made the problem even more difficult for the programmers. Because now we've created this asynchronous model that they have to think about. How can I return to the user and say, your check has been deposited? I can't. I have to say, your check has been received. And we've got to write all this other code to figure out, when your check actually gets deposited and all these other things, okay? Idempotency keys is the other approach that I see. And there's some companies that have really leaned into this. So Stripe, I think, is probably the best example, where you can make every single mutating call to Stripe with an idempotency key. What an idempotency key is it literally lets you say, when you make the call, it lets you say, hey, I want to identify this mutation with this key. So if I ever make this call again, for example, because I have a network error, and I retry, that system can say, oh, nope, we already performed that mutation on your behalf. We won't perform it again. Okay? All right. So what do we do in Reboot? In Reboot, we tried to make idempotency first class. So what does this look like? So we're going to go back to the front end. Imagine the front end's making a call. It's constructing an account. And then it's calling, say, deposit on that account. So it's actually this part of the code right here. So we're going to give Andy some more money. Actually, we're going to give me some more money. We're going to give me another 100. I'm going to call deposit. You can see I did that. The numbers went up, 233 to 333, so forth and so on. Now, what's powerful here is that what we did in Reboot was by making idempotency be a first-class concern, it means under the covers, you can call something idempotently, and the user's code doesn't have to change. So if we look at deposit, it's a really basic function. I'm just going to increment my balance and return. That's all I'm going to do. Now you can imagine in a real enterprise system there might be some other stuff, but things I'm not doing are things like checking to see if the idempotency key that you passed to me is something you've passed, and then I need to do something. That's all completely taken care of by the runtime. And if I go back to the front end and I look at actually the code for calling deposit, it literally just looks like me just calling account.deposit and passing the amount, because under the covers we can make sure that, that we're using the idempotency keys. So I want to show where this becomes really, really valuable. So what I'm going to do is I'm going to go back up and I'm going to sign up another user. I'm going to sign up myself. But I'm not going to click sign up just yet. I'm going to go back to my development environment where I'm running. I'm actually going to trigger a K8s monkey. And then I'm going to click sign up. And you'll see that now I've clicked sign up and I've got this little spinner, right? Because in the back end, K8s had occurred, which is exactly the cases where I care about wanting to retry. There was just a network failure. It doesn't mean that the event didn't occur. But I'm guaranteed now, thanks to idempotency, to be able to call this thing as many times as I want. I can call this mutation as many times as I want in the face of network failures. Now, these are not just going to be failures coming from the front end to the back end. These are all the calls between all the different microservices in the back end as well. So by making idempotency be a first-class primitive, we're starting to eliminate that paradox and giving people the opportunity to just say, like, yeah, just retry. Retrying is always safe. You can retry. Okay? Again, dramatically simplifying the experience for developers. Okay, all right. Last one, weak consistency. Okay, what do I mean by this? So to talk about this one, I want to, again, kind of zoom to 100,000 feet, talk about an example, and then dive deeper. So we're going to look at a typical e-commerce checkout that you'd build with, say, microservices or Lambdas. You've got some checkout function. This is actually effectively a gRPC code. What does this checkout function do? It calls into the cart to get all your items. Then it calls into shipping to make sure you can ship the order, maybe gets a quote. Then it calls into the payment to authorize the charge, calls into the shipping service to ship the order, or back to the shipping service, calls into the cart to empty the cart, and then calls the email to send the order confirmation. When we first look at this code, there's a lot to really like, right? This is the dream of microservices. I've broken up all of this different modular stuff into the pieces that allows me to call it. Independent teams can own all these different pieces. You know, like, what's to hate about this code? This is awesome. But there's a massive bug in this code. Can anybody tell me, like, what's the problem with writing code like this? What happens if the machine that's running this code fails right after I call payment.authorize charge? Right? And the truth is that anybody that's run microservices in anger, so all these companies that we worked with when we moved, you know, broke up their monolith and moved them to microservices to run things, they would never write code like this because they know the danger of what would happen here. The intent when the developers actually wrote this code is that it would get executed atomically, that all this stuff would happen atomically. That's what they were used to when it was a monolith and they sent a single transaction to the database, right? And of course, if somebody retried checkout, it would be idempotent, which was the thing we already talked about. You know, we're just trying to build on our foundational pieces, okay? So when I show this example, I think there's kind of, there's two people in the audience. There's some people in the audience who are sort of like, yeah, Ben, like, of course, nobody writes microservices like that. Obviously, you know. And then there's the second people in the audience that are like, oh my God, I am pretty sure my code in production totally has this bug. I wonder what I should do about it. And it makes sense that a lot of us fall in that second camp because this example, this checkout example, it literally comes out of Google's microservices demo. So like anybody starting to learn microservices from Google's microservices demo, which is where most people start, are doing it wrong out of the box. And this is what I'm talking about with the program abstractions that we're giving to people. They're not great abstractions, which require us to have to do all this other stuff. And these are real bugs. Again, I try to take screenshots when I can. This was me trying to book a flight. I got an unable to complete transaction, and I was like, ooh, maybe there's a bug here. So I clicked OK. I tried with a different credit card, thinking like, hey, maybe it's my credit card. I tried 4 times. Okay, never worked. I was like, okay, United is down. I'm just going to move on. couple hours later, I happened to look in my inbox email, and I had 4 emails from United Airlines. I was like, whoa, that's suspicious. An important message regarding your reservation. I had 4 reservation numbers, each email telling me that the other flight that I tried to book potentially conflicts. Like I was trying to book the flight 4 times. Like we all know what happened, right? Like somebody had some code like this, we got through, we executed the thing that said, give me a new reservation number. I got the reservation number. We executed the other function that said, hey, can you check to see whether or not this reservation might conflict with something else? If so, send them an email. I did that part. Then we got to the, hey, let's process the credit card, something failed. Oops. Guess the user's going to get that other stuff. These are real bugs. So what's the state of the art? Back to queues. Rather than actually being able to make the calls between each of the individual things, what we have to force application developers to do is actually write to queues and then read from queues. The queue being the thing where we can get that guaranteed writes, like, hey, do this thing only if I can do that, so forth and so on. We implement these saga patterns. More so now, we start trying to do durable execution. It's becoming a term that's really trying to solve like this particular use case when you have some kind of a workflow that you're trying to execute. Okay? Now, what's interesting is this is really bad. This is, the inconsistent state of the world. So I talked about it being weak consistency. This is literally inconsistency. This is really, really bad. But with all these tools, we're basically giving developers, queues, pub, sub, sagas, durable execution, it's really just moving them from a world that's inconsistent to a world that's eventually consistent. Because while I'm still stepping through each of those phases of my workflow, I haven't converged on some final result. So it's an eventually consistent model. And it's led us to, what we talk about when we look at people's architectures, to talk about as being queue glued. Like your software is queue glued. And it's back to this inversion of control. And there's a reason why modern languages like TypeScript and Python have async and await that were added to them. It's because people don't like to program with callbacks. And that's how we're building all of our distributed systems with microservices. If we're using queues, we're writing something to a queue, and then we're executing the callback for that queue. And then we're writing something else to a queue, and then we're executing the callback, so forth and so on. Again, some of the systems like durable execution are starting to help with some of that, but it's still eventually consistent, which is ironic given all the progress we've made making distributed, strongly consistent databases. We've got all these, this amazing work that's been done, and yet our applications are still eventually consistent because of the queues, the event sourcing, the durable execution, everything else that we're running. All right, so that's the state of the art. Queue, saga, durable execution. I hate sitting down with a company when they're like, okay, now I'm going to have to implement all this to do it safely. Many don't. Many just have these bugs waiting to happen in production. But for the organizations we work with, we say we have to do it. So again, it was a big thing that we wanted to solve in Reboot. So how do we solve it in Reboot? We gave people first-class distributed transactions across all their functions. Okay, so what's that look like? Let's jump back to the code, and let's look at transfer. So transfer is exactly what you can imagine it is. It's something where, say, I want to go ahead and I want to transfer, I'm going to take some of Andy's money. He's looking really flush right now. We're going to send it to me. We're going to go ahead and take $100. Okay? So this is an operation where I might want to be touching 2 different accounts simultaneously, right? And I'd like this to happen where both accounts get updated in a strongly consistent way, not one account gets some money and then the other account doesn't get money, so forth and so on. So I can do that by effectively, it's a different kind of qualification. We saw readers, we saw writers, transactions is one of the last ones. And it lets me write this really, really simple code. So now I can write the code that I wanted to write where I can get references to these other account types. I can call withdraw, I can call the deposit, and either both of them are going to have executed and the money will be moved, or none of them will. All right? And in fact, I wouldn't write it like this. I'd actually write it the way that we did it in the code here. I'd run withdraw and deposit in parallel. Because I can, that's kind of cool, right? Like, I have a guarantee now that these things are going to happen or they're not going to happen. In fact, giving transactions as a primitive to developers building cloud-native apps it lets you rethink the way you'd write a lot of your code. So if we go back to this checkout example, what might checkout look like in, say, reboot? Well, I need to call cart to get the items, and then I need to use those items to prepare the shipping order, but then authorizing the charge, actually shipping the order, emptying the cart, and sending the email confirmation have no more data dependencies, so I can execute them all in parallel. So while, of course, introducing something like distributed transactions is going to be, it's not free, right? We have to pay for it. We can actually write the code in a far more efficient way. Instead of 1, 2, 3, 4, 5, 6 round trips that are probably hitting databases, because that's the way microservices work, it's 1, 2, 3, plus whatever work we need to do for the distributed transactions. Okay? All right, so some of you might be thinking, though, and by the way, did you check your email? Did you get an email from us when you signed up? Hopefully you did. If you didn't, don't tell anybody, because that'll ruin the demo. You got it. All right, great. So some of you might be thinking, like, hold on a second, Ben. You're doing external effects. You're sending people emails. Like, how do you atomically or transactionally actually do external effects? And the answer is it's really, really hard, because almost all third-party APIs that you try to talk to today, they have no notion of a rollback. They have no notion of like participating in some kind of a distributed transaction. And many of them are not even compensatable. So compensatable would be something like, I can't undo it, but I could change it, right? And one way of changing it might be to, instead of having a seat reserved in an airline, I could have no seat reserved in an airline, and that's effectively my undo, right? Many of them are not. So to make this work in a system like Reboot, we have to think more creatively. And the observation or insight that we really have is that most of these third-party APIs, well, they don't have a rollback or compensation. Many of them have a dry run. So many of them have a way of actually checking to see if this would actually work. And if it does, then we feel pretty good about the fact that we can complete our reboot transaction. And then afterwards, we can go ahead and we can do the actual third-party external event, but now it will have eventual consistency. So we'll have strong consistency of all the updates within Reboot, and then eventual consistency of the work that we do externally. And honestly, I think that's the best that we're going to be able to do until maybe in the future we could get more and more companies out there trying to think and adopt these kinds of protocols. How amazing would it be if I could call into your service, because you provided an API where I say, hey, I'm trying to do something transactionally, and your service could say, okay, great, it could be part of that transaction, that distributed transaction, so we can safely do these kinds of updates. It's a dream, it's a future. I think we can get there. All right, now, one of the questions, okay, great, I got 5 minutes. Okay, great. Great. All right. So one of the questions then is like, okay, well, how do we run these things that are talking to the external services? Because I told you we already try to run things like readers and writers and also transactions. We try to execute them multiple times to make sure you don't have any side effects. But now I actually want side effects. So where do I do my side effects? So you do side effects in the last qualified function type, which is a workflow. Okay. And a workflow is something that, unlike readers, writers, and transactions, that don't have side effects and that are atomic. Workflows are not. They're not atomic. They're eventually consistent. They're the scariest place to write code in Reboot. The way we write all code today in all other frameworks, that's the mental model we have for all of those things. And really, they're the place that you only go to when you want to think about doing external effects. But one of the things that we do is when you actually run a workflow, we retry them upon failure. And so here's kind of the interesting mental model to think about there, which is if you want to send that email to Mailgun, you're using Mailgun, some external thing, you probably want to retry if there's a failure. You don't have to retry if you're doing transfer or something else like that, bank transfer, because the front end can retry. You can push the retries all the way out to somebody else. But if somebody's saying, hey, I want to make this external effect on some other thing, you probably want to do your best, since the other transaction is committed, you want to do your best to actually make sure that thing happens. So we retry. And the mental model that I think is really interesting here is it makes you start to think about the way you write your code as this idempotent convergence. I'm just constantly trying to retry all the pieces until I converge idempotently on a good state. Okay? All right. Workflows are the closest thing in Reboot to something like durable execution, which I think more and more people are looking at for doing workflows. But there's no replay logs. There's lots of really interesting things that make them nicer when it comes to updating your code and dealing with a bunch of the pitfalls that we have from those. All right, so you can play with all these examples. You can change your code. You know, if I were to go and make a change to my code, the local environment, you know, we tried to make it like a great local environment experience where it finds your bugs and it does other things. So workflows are actually how we were doing interest. So here is interest. It's like I said, the world's best interest, where every 1 to 4 seconds we go ahead and we increment your interest. And it's just a workflow. It's just a long-lived process that's running in the background that I can schedule, that I can run, that's doing the stuff. Okay, so let's reboot. It's just data and functions and a well-defined semantics for how functions are executed and composed together safely. We call the encapsulation of these data and functions durable data structures. And that's the higher level abstraction that we're excited about trying to bring to the cloud-native ecosystem. Getting people to think about building things durable data structures, not microservices, not lambdas, durable data structures. Instead of thinking in tables and rows in a database, you think in terms of these durable data structures that are distributed. They're partitioned by default. You're not thinking about the deployment part. You're just writing the code. It's all getting run for you. Thanks to that model, we have first-class reactivity, and first-class idempotency, which makes building full-stack apps so much easier, and first-class transactions, which makes it so that on day one, you're not going to run into all the bugs that you would have run into if you're just picking up microservices off the shelf. Yeah, so the future, you know, I think that cloud native is ripe for building higher level abstractions, letting people focus on the business logic, not deployment. It should scale when you need it. It should be full stack ready, and it should be safe by design, even though it's distributed. If you're interested, you can check more about Reboot at these places, and thanks for coming and listening.